Great, thanks. I want to thank the school for allowing me to present some of my work. My name is Urquía. I am a PhD student here at Copenhagen University. I am presenting my thesis in exactly 44 days, so I have no pressure at all. I'm not a first-year student like most of you. I have the very ambitious task of presenting 3 papers in 10 minutes, so you're going to have to bear with me for a second. Now, we know the Standard Model was finalized, the unification of electroweak interactions was finalized in the 60s by Weinberg, Salam, and Glashow. Glashow, by the way, was a postdoc here when he developed the theory of electroweak interactions, in case you didn't know. Now, so far, it works great. We have found no seeming anomaly, except for a lot of them. The big one that I'll focus mostly is the fact that the Standard Model cannot account for neutrino masses or neutrino oscillations. So one of the simplest ways in which you can do this is by simply adding the right-handed neutrinos, which Jorge and Mariam was talking about yesterday. So you add the right-handed singlets, and after spontaneous symmetry breaking, what happens is that the right-handed singlets and the neutrinos will mix with one another, and then you get this famous seesaw mechanism. And in the minimal model, we expect the masses of this right-handed singlets to be at least GeV. So that's why we call them heavy, because they're relatively heavy, they are neutral, and they are lepton. So they call them HNLs. And in HNLs, we care about basically 2 different parameters. We have the coupling of the HNLs have 2 electrons, muons and taus, and then we have the mass. And the lower you go in coupling, the more feebly interacting they are. And so there's a lot of ways in which you can probe this. These are all the direct probes that we know of in the most minimal model. And if you can see, there's a huge difference between what happens when you go before 100 GeV and above 100 GeV. Because below, you can probe it directly, but above, I mean, there's no real experimental way in which you can probe that. So the best way that we can do is actually examining indirect measurements. So when you add HNLs to the Standard Model, what happens is that you can get such processes that are not allowed in the Standard Model. For example, muon decaying to electron and gamma, muon decaying to 3 electrons, muon conversion in nucleus. And this has been known since 1976, okay? So I'm not bringing anything that new to the table. And what happens here is that, HNLs can mediate these processes by running in different kind of loop diagrams. So these are some of the loop diagrams that, for example, in Z decaying to muon and electron, for example, can happen. And the one that I want to focus on is this green guy here. And this phi, I mean, it might not look like a Standard Model particle, but it actually is a Standard Model particle. It's a Goldstone boson that eventually gets eaten by the W. You can work with the Goldstone bosons, and what happens is that the coupling is much more like the Higgs. So this coupling will depend on the mass of the HNL, and this coupling will also depend on the mass of the HNL. So you end up with this green term here, which depends on the mass. So the branching ratios of, for example, mu to 3 or mu to, or muon conversion in a nucleus actually will depend on this parameter, not mu to gamma, because there's no set bosons there. And so this is important because previously what people were reporting in the literature when talking about the bounds from these processes were something like this, when in reality, maybe it should grow like this. Yes, so this is more or less the first idea of the first paper. And then now some work in progress that I'm doing so far is to examine the same things, but with processes involving mesons. So tau decaying to E and rho, tau decaying to E or omega, tau decaying to 1 meson, 2 mesons. And we find that at least in the tau sector, these are quite competitive, if not beating some of the other processes. Yes, I mean, there's more to come. I have like 50 plots made already in my computer. I'm not going to show them all. But the other part that I wanted to talk about is this line. So this line is the perturbativity line. And we wanted to examine where exactly this perturbativity line coming from. And the way that you can probe this is, okay, when does perturbation theory begin to break down? We expect that big coupling means you cannot use perturbation theory anymore. And the coupling that we're looking for is the Yukawa coupling. And one probe of perturbativity is by examining the S matrix. So we expect the S matrix to be unitary in any quantum field theory that's renormalizable. So it should always be that in any processes the S matrix has to be unitary. And the way we can probe this is by computing the partial waves or the we compute the amplitudes, which, I mean, they're proportional to the S matrix, and then we compute the partial waves. And the partial waves have to compute this set of inequalities. So we compute a set of 2-to-2 scatterings that are all proportional to Yukawa couplings, and then we see, okay, when do these set of inequalities begin to break down? And we look, for example, I'm going to show just two results in J. J is the angular momentum that was transferred. So we look at these two set of scatterings, which give exactly the same results because, you know, leptons and neutrinos live in the same doublet. So you compute, they give you both the same results. It actually has to be Yukawa total. I will not explain why, because that's going to take me like 5 minutes, but you can write everything in terms of the total coupling of all flavors. And in the end, it gives you something like Yukawa has to be less than or equal than 8 pi, which is comparable to the, I mean, okay, because people in the literature were presenting this bound, which this is the decay width of the HNL, and it was 4 pi, so it's different up to a factor of 2. I mean, you can divide it by 2, that's okay. If you want if you want to be a little bit more safe. So this is a little bit of a more conservative bound. But then we're looking at the J equal 1 results, and here you have to consider all this set of scattering. So everything in the left here can go and everything in the right here. And I didn't said something. This inequality only applies to elastic scatterings. Yes, it's here. So these are all elastic scatterings, and what I mean is that the initial state has to be the same as the final state. And here, I mean, like this going to this is not an elastic scattering. So what we do is that we write everything in a matrix. So here are the initial states, here are the final states, and we put them together. And if we want some elastic scatterings, we have to diagonalize this matrix and use the eigenvalues. And before we notice, we have a 1 plus square root of 5, and then our bounds give you 8 pi over golden ratio, which is a funny number. I don't understand why this is here. but it was funny when I saw it. And okay, where's the new perturbativity line? Okay, it doesn't move that much. From 4 pi to 8 pi over golden ratio, it doesn't change that much. But it's still a fun academic exercise and a fun number. Okay, I mean, that's all I had to say to you. Then these are my things.
Thank you, Kevin. Questions? Yeah.
Okay, hey, I didn't quite understood why you need to explore perturbative band. Like, is it related to heavy mass or?
Yes, because at least we want to know exactly when, for example, okay, I didn't say that, yes. But we want to know, for example, when the bounds for these CLFV processes begin to break down. Okay, I would say after this line, maybe you cannot really trust these bounds, although our referee to this paper was a bit angry about this. And okay, but it's a probe as to when we cannot really trust these computations, let's say.
Okay, thank you.
Any other questions? Not the case? Then let's thank Kevin again.